Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
So first and foremost, I want to do an introduction to the concept of high-speed design. And then secondly, I want to spend some time talking about Altium Designer's signal integrity tool, which is in the program. You already have it there. Many people have kind of dodged around it because they don't know what to do with it. And today I'm going to talk about how to use it. One of the things I wanted to add to Brett's list over there, and something I've been thinking about for a while, what is the value that we provide to our customers? Well, we can show you functionality. But what I have found ultimately is that in addition to functionality, we also want to show you the methodology, because Altium's got some great stuff, but if you don't understand the methodology, it seems like it's all over the place and it's fragmented. And if you understand how they set it up, then you'll have an understanding of what Altium was trying to accomplish with their tools. With that being said, I need to dispel a myth, and it's a myth that I bought into even when I was at Altium, that Altium could not do high-speed design. And in fact, our competitors picked up on that and said, yeah, you don't want to use Altium. Altium can't do that. That's quite frankly, it's a lie. My mentor, Dr. Jonathan Friedman, Mike Harrington, and many others who probably sit in this audience today who know more about high-speed design use Altium to do high-speed design. So therefore, if they can do it, we can do it too. But we have to dispel another aspect of that myth, and I think a lot of us look at high-speed design as being very much like creating analog design, where analog requires the knack, it requires the feel, right? If we've all been through that and say, kind of, analog seems hard, and we always go to withdraw from that end of the electrical engineering spectrum to the digital design area, and we talk about, and we get ourselves involved in digital design, and we get ourselves involved in programming because it's very strict. Well, I got news for you. High-speed design is very strict as well. And yeah, there's some science behind it, and there's a lot of analog science behind it, but it actually boils down to a set of rules that you can't break. And that's kind of good for us people who like to have that yes and no, that Boolean type of logic in our design. You've got to follow the rules, and you'll get exactly what you give it. And you're going to see this as we're going along. So don't think of high-speed design as being this wild art form where anything goes. It's actually very restrictive. There's 6 ways to do it, and 5 of them are wrong, right? So that's what we're going to take a look at. Now, what is high-speed design exactly? Because people ask this question as to where does high-speed design start? And Dr. Jonathan Friedman, when I was talking to him about it, says that's kind of a trick question because it's not about the speed in which the total signal is propagating from point A to point B. It's actually about the rising edge of the square wave, or the rising edge of our wave. Okay? In the real world, in the natural world, we have sinusoidal waves. And if you look at a sinusoidal wave from a frequency point of view, it's only one frequency. But when you look at a square wave, it's artificial, it's man-made. It actually has a number of frequencies that are built upon it. In fact, what you see over here, it's a great example that I found on the internet here from this company, Sabratech over here, and I hope I didn't pronounce it incorrectly. But they had a great example. We're so used to looking at waves from the time domain. But when you look at the frequency domain, look how many frequencies were involved in making this line, right, this rising edge. That's a lot of frequencies. That's a lot of energy, all right? And so we have to keep that in mind. So what we're dealing with here is a lot of frequencies with a lot of energy. And what that ultimately talks about, or where we start actually hitting a real limitation, is what they call the wide bandwidth. How much of this frequency can we handle before we just have too much noise, too many things are going on that degrades the signal or just turns it into mush. Okay? So that's the key thing we got to understand is what frequencies can we handle on this rising edge? How fast can we make this rising edge move for us? And so it's all based on that rising edge. In theory, a 10 megahertz signal, all right, which is not that fast in our mindset, if it has a super fast rising edge, that's actually considered to be high-speed design. Okay, so just some food for thought on that. And so I'm going to jump over here to the next slide. All right. The reason I want to show this very early on is because this plays a massive role in high-speed design. So the question is, how come it works in a low-speed design, but it doesn't work in a high-speed design? Why is it like, if for up to this point, I've done boards for years, why does high-speed design all of a sudden have all these additional things that I didn't have to worry about before? Well, what Dr. Riazi did, and I don't know the man personally, but he has some really great articles on the internet, and this is one of them. What he did is he wanted to show what the field effects were when something is propagating from point A to point B. And you got to keep in mind that when we're dealing with electrons going through copper, we've got two elements. We have the electrical element, but we also have a magnetic element as well. And that magnetic element has to be controlled, right? There's currents that get pulled up as we're doing. Remember inductive currents in physics? I try to not remember it, but that's one of the things that we have to deal with. But in slow speeds, that gets propagated over a long area. And that's what you're seeing here in slow speeds. But in high speeds, what happens is those fields actually concentrate right underneath that signal. All right? And that's a lot of energy, a lot of concentrated, that's basically current. That's a lot of energy if you think about it, that's going directly underneath your signal as you're going from point A to point B and high speeds. And we've got to make sure that that path exists. Because if we don't, it gets ugly. So what does that mean? Well, that means we've got to control a few things. And it really boils down to two aspects and its relationship. Number one, the environment, which is your stack up. And you'll be surprised that that's where 90% of your issues are going to start, is in the stack up. It's one of the things we got to look at immediately. In the past, who cared? But you'll see in a minute that the stack up plays a huge role. The second thing is the geometries, the traces, and the rules. Altium has the rules. You just got to know how to set up the rules, because the rules will impact the traces and the clearances and the widths. And it will also bring us to the next thing here, which is the impedance. We're going to hear this all the time, this thing called impedance. Right? So we got the environment, again, our stack up, our geometries, our rules, and our traces. The relationship between it, we get this thing called the impedance. And impedance is about two different things. Some of it's Altium's responsibility. Some of it's your responsibility. The matching is your responsibility. That's basically through the correct DRC setup and through the data sheets. But once these are set up, the maintaining through the layer stack up and the DRC is Altium's job. It's supposed to flag you saying, hey, you told me that you can't have this, right? Because the rules that you set up should be based off of high-speed principles. Well, we can try to ignore it, but the fact of the matter is the science is going to catch up with us. And how is that going to impact us? Well, it's going to be radiation or in the form of electromagnetic interference. You're going to get reflections, which can ultimately damage buffers. And then lastly, it's just going to be a crappy signal, right? You can send stuff down the line, but if the receiver can't read it, what good is it? Or you're going to have, a compromised line, or you're going to have compromised data, and that's not what you want. Okay? So let's talk about the layer stack-up, because the layer stack-up plays a massive role in both the integrity of the signal and the noise mitigation. Now, it's not the only thing. There's other things you got to do, but this is where it starts. And the analogy I like to give is if you can imagine for a moment you're building a house, and you decide, I don't want to put down the foundation. Concrete's too expensive. It takes too long for them to get there. I just want to build it. Well, the problem with that, as you probably know, it doesn't matter how good the materials are that you use for the house or how good the contractor is going to be. The weather, the elements, the pests, everything else is going to impact that house from day one, so that house isn't going to stay up very quickly. It's going to deteriorate, it's going to decay, it's going to cause constant need for upgrades and repairs. Well, the same is true for a PCB, that it begins with the layer stack up. Okay? And that's, I think, new for a lot of us, because in the past, it's like, let's start off with 2 layers, and if we need more layers, we'll throw some more layers in. If I need a ground plane, I'll throw in a ground plane. Maybe I can use the polygon pour on the top to help me with the ground planes. And in the low speed, that's fine, because that's a cost factor. But when we're dealing with high speed, we can't get that simple with it. We actually have to deal with the layer stack up front. Okay. Now, as I mentioned earlier on, there's 2 things that we have to deal with. We have to deal with the environment, and we have to deal with the geometries. And maybe the question came up to you as well, okay, you've talked on a high level, let's get to the nitty-gritty over here. How are they impacting each other? What I'm showing over here is a model. This is the impedance model. It is an ugly equation. But somebody at some point down the road, because Freescale and Altium both knew the equation, someone must have taken boards, put out different traces, did a whole bunch of different experiments to create this particular model. Okay? And what they did was they looked at all the different factors that were playing a role in this impedance. And what they found was a couple of things. They found 4 major factors. They found the trace height, they found the trace width, they found the distance from this signal to the plane, and they also said the dielectric constant, because effectively we have over here is a capacitor. Okay? And so that's what they came up with over here. What's interesting is a little side note, the length isn't playing a role in this equation. Now, it's not to say that you can ignore the length. Length has all its other issues altogether, like coupling issues, and maybe we can address that at another webinar. But for the purpose of impedance, length does not play a role in this, believe it or not. So why am I bringing this up? Do you need to learn the equation? No. What I'm trying to bring to you is this relationship, that the layer stack up literally handles 75% of the factors of the impedance. The trace height you do in the layer stack, the trace to plane distance of the layer stack, even the layers that you set up. The only thing that we did, the dielectric constant. The only thing that we seem to have a little bit of slack on is the trace width, but even then, if we want a specific impedance, the width is tightly controlled. So all 4 factors, in order to have good high-speed design, are very tightly controlled. So again, it goes back to what I said earlier on. High-speed design is not this kind of knack thing that we try to do with analog design. It's very rugged in its requirements. Okay? So that's what we've got there. Now, I would like to have shown this in Altium Designer. The reason I do this is because the dialog boxes lock each other out. So I want to show how all these things play together. Let's start off over here with the width rule. If you're familiar with the width rule, you know that normally it's asking for a preferred min and max length. All right, but there's a little checkbox over here called characteristic impedance-driven width. And if we click on it, Altium will change this into ohms. Now, if you do that over here, and assuming you've set up everything in your layer stack manager, including the thickness, including the dielectric constants over here, all right, and this information over here in terms of what the impedance is, it can actually put this into this equation. There's a little button in the layer stack manager called the calculation, and if you click on it to the bottom left, bottom right, and it gives you these equations over here. And by the way, they're also part of the query language. So if you don't like what Altium has or you need to modify it, you can go in there and actually make the changes. And if you need to ever change back, there's always a default button there. But the fact of the matter is, if you tell what you got here and you've given the information in the layer stack, Altium will come back and give you recommendations for each one of your layers. Okay? So that's a pretty slick little capability that Altium has available to you. Now, with that being said, you'll notice that this over here, if you can see, it says 40 mils. That's really outrageous, right? We're used to working in 8 or 10 mil traces. If we're going through FPGAs, it's going to be even smaller than that. So what happened over here, and that brings us to our next point, all right? Reference planes. We've got to have reference planes. That means that, because I showed you at the very early onset, I showed a picture that's very similar to this, that and under high-speed designs, you have a lot of current that's flowing directly underneath that signal, okay? And that's necessary because of the amount of energy that's going from point A to point B. It's got to basically be, dispersed, right? What they show over here, and again, if you go back to Dr. Riazi's article, what he did was he says, okay, we're going to take a piece of copper out of here and show what happens when you have a trace that's going high speed and where the currents have to basically redirect or go in order to compensate for that. And what happens here, and by the way, it's not that these are jumping over. What these arrows are just indicating is that that the larger the arrow means the stronger the current is, the more energy that you've got basically going. But it hits basically almost a wall, and it's got to literally find its way around in order to continue to follow that trace that's going about. Now, if there's nothing there to follow, it's basically like a car going 100 miles an hour into a wall. The car ain't moving anymore, the wall ain't moving anymore, but that energy gets turned into something else. It gets turned into noise, it gets turned into heat, it gets turned into metal movements and deformation, right? So that energy just doesn't disappear, right? Energy is neither created nor destroyed. So what happens to it? Well, as Dr. Riazi mentions, if you have current diversion, meaning that current had to go around something because there's no copper, it's going to lead to crosstalk. most importantly, this thing called EMI, which is basically noise, and also even rise time degradation. All right. Now, why do I mention this? Because what a lot of people are going to try to do to try to save on layers, they're going to say, well, I'll put a polygon pore on the top layer. Well, if I got a signal where my cursor is, and I've got one on the other side, and let's say it's on another layer, and I was going to use my top polygon pore as my reference plane, look at all the breaks they've got in that copper. It's not clean. It would have to go around, and therefore you have a ton of noise. Now, what I'm not saying is that you should not have polygon pores. Polygon pores are very important on the top and the bottom because they basically help to create a Faraday cage for that particular board, so that board itself isn't ringing like a bell when you have it with other bells in a system. But from a signal integrity point of view, you're going to have problems. There's going to be noise, and you're going to have signal integrity issues because it needs to have that reference plane. So don't use the top polygon, especially if you're using all the copper traces on there, because it's too fragmented. All right. And in fact, if we look at this, here's an example of what a lot of people try to do, and this is not the way to approach this. What they did here is they said, well, let's put 3 signal layers over here, 3 signal layers down here. We'll throw poly on the top, throw poly on the bottom, and we should be good to go. Well, no, this is not going to work, okay, because this top layer over here is way too far away from this reference plane, and the things that are propagating, or the signals propagating in mid-layer 1 and mid-layer 2, they're all going to interfere with each other. So the signal quality is going to be very compromised. That's why when you saw the layer stack manager early on, it said 40 mils because of the way this was set up. Okay? So a proper way, or a way to do this, is an example that Intel provides here, that you always want to have a reference plane nearby your signal. Okay? So here's a signal, here's your reference plane, here they are put between them. And it doesn't necessarily have to be a ground plane, by the way. It just needs got to be a solid piece of copper that energy can just run down as your signal is going from point A to point B. So if you want a 6-layer board, you can do it. This is just an example of one I found through Intel. Okay. Now, I'm going to jump into another topic over here, but I think you can see at this point the necessity of really thinking about your layer stack up as the foundation for high-speed design. Now, the second element of that we'll talk about today is what we call signal integrity. And signal integrity is simply the quality of the signal. So, yes, we could set up our layer stacks correctly, but if we're not doing our job, right, which is the maintenance or the maintaining of the signal, we're going to have some issues. Now, when we deal with signal integrity, we can do simulation. Simulation comes in 2 different forms. One of them, I hope you've heard of both of them by now. Certainly one's SPICE, which has been around for a long time, actually longer than I've been alive, which is amazing for a language to last that long. And then there's also IBIS as well. And IBIS has been around for quite a long time, but may not be as well known. So let's take a look at both of them here for a moment. And in particular, let's take a look at SPICE. So SPICE is very accurate. It's an amazing tool that came out many years ago for its time, but there's some disadvantages of it. One of the issues is the way they code structured it. If you're familiar with the old code, so when I went to the university, I had to actually draw up the circuit and then put the nodes in each one of these. The newer tools, they'll let you draw it, which is really nice. But this is what the code is underneath it. And so if you've ever played with SPICE, you know that the prefix on the first character of every line represents what they call an element. So this over here is a capacitor. This is another capacitor. This is a diode, so on and so forth. And that's a very rigid structure. Okay, you say, well, what's the big issue? Well, this was a free tool that got dispersed across, all the industry. And certain companies like PCAD or Microsim at the time took that, and they added things on there that Berkeley didn't know about. So when Berkeley put their stuff out, they actually had competing elements. So now you have divergence in the code. And it's actually very important for you to know if you find a model, where is it going to work? Because it may work in Berkeley SPICE, it may work in PSPICE, it may not work in one, it could work in the other, and so on and so forth. So that's one of the big issues you got to deal with because of the code structure. But there's a bigger disadvantage. Manufacturers don't like to provide them anymore. Why is that? Because their intellectual property is in those, they're in there. Now they can encrypt them, but a lot of people can't read the encryption stuff. And what you find instead is that companies like Linear Technologies and Texas Instruments say, look, we'll give you a free tool so that you can do SPICE. Why do they do that? That's so they can hide the proprietary information. Sure, you can draw other stuff in there. Sure, you could do SPICE in there if you want to. If the model will work in there, bring it on in. They don't care, but they are not going to show you the proprietary information, and that's why they're providing you the tool free of charge. Okay? So the whole SPICE situation is kind of getting a little difficult just because of some of these code limitations that we're starting to come across. So let's talk about IBIS. Because what we're doing high-speed signal integrity, we're not trying to really simulate the design. We know the design will work. What we really want to know is the signal's integrity going to be correct when I go from point A to point B? And if you ever look at an IBIS file, it's basically nothing more than an IV curve. So someone went into a lab and says, all right, let me do some tests over here and let me write down some numbers. And that's all you're doing is you're just feeding Altium an IBIS file that's full of voltages and their corresponding currents depending on whether it's typical min or max. It depends also if they want to provide that as well. Okay, so you can open up an IBIS file very easily. This is what it's going to always look like here. All right, and that's what you got. And by the way, it does stand for I/O buffer information specification, because again, what the company's coming back saying is we don't want to show you the guts, and you don't need the guts of what we're doing. We just want to show you, for the purpose of signal integrity, how that buffer is going to respond. All right, let me move on to the next one over here. All right, so what about Altium Designer? So you can add models to Altium Designer, IBIS models, in the same fashion as footprints, whether in the library or in your design. You can run signal integrity in just the schematic capture alone. So if you're just working on your tool and you just want to see reflections, you can do that, okay? But if you want the full functionality of the tool, you really do have to have your PCB completed so that it can add the trace information and its spacing on the traces as well. And so with the PCB, if you got both the schematic and the PCB, signal integrity can do both the crosstalk and the reflection. Okay? And then there's also a special manager for FPGAs. So keep in mind with FPGAs, the user gets to control the buffer types, like the technology for the buffer types, the slew rate for the buffer types, the current capabilities of the buffer types. So unlike other ASICs where those are fixed, the FPGAs have options. So Altium provides you a special tool for that. And then lastly, Altium has to work with internal planes. Now, there's workarounds to that. So if one of those fans is saying, I like to do a single plane with a polygon pour, this won't work for the width rule that I showed earlier on, and it won't work for signal integrity. But what you could do is you could put the internal planes in first, do your signal integrity, then remove them, and then add those pores in if so desired. But keep in mind, too, it may sound like, hey, why don't you just do it? It'd be easy. But again, there's going to be people who are going to try to put signal integrity or handle signal integrity by doing polygon on the top and the bottom, which is going to be very fragmented, and that's going to cause a lot of effort for Altium to do a tremendous number of calculations. And I mean, at that point, it's going to be heavy-duty calculations that I'm not even sure how they would be able to address at this point. So that's the only reason they're not doing polygon pours. But there's workarounds by using the internal planes. Okay. And that's my presentation there. So let's get to the fun stuff. Let me bring up my Altium Designer at this point in time. And so I have a design. Now, let me preface this by saying that Altium does have a tutorial on signal integrity. In fact, what I'm going to do is walk you through this very quickly. If you're interested in this tutorial and you want to go through it slowly and kind of get a feel for all of the features and functions and capabilities of it, please contact one of the 9-Dot representatives, either Jason, Christopher, or Brett. The reason is that, yes, you can go on techdocs@altium.com and you will find a tutorial, but the files do not match with this. They made changes to the FPGA that were corresponding to this. They added in a different SRAM. They added a few different things in, and they did not update the, they provided the new files, but they did not update the documentation. So we've got the complete corrected set. That's why I gave kudos to Derek, because he was the one who helped me out make sure that we could provide this tutorial to you. That's Derek Jackson from Altium, who I'm referring to. So let me walk through this, and again, it's going to be kind of a quick walk, and there's probably a lot of different things that you'll be curious about, but let's take it where we can. So what I want to show you first and foremost is this: how do you put an IBIS file in? So I'm going to hit the J key. That brings up what they call the jump pop-up, okay? And I'm going to use something called jump component. Now in this design over here, U5 happens to have one of these IBIS files, okay? And by the way, I should note, you don't have to have an IBIS file for every single device in here. You just have to have IBIS files for those things that you want to test for signal integrity. So it's not like SPICE, where SPICE requires something for, it requires a model for everything, or else you can't do it. But signal integrity says, like, look, if you got it, I'll test it. If you don't, I'm just going to skip it. All right, so it did find it here, and I'm going to double click in. And you'll notice that the model is listed over here where the footprints and the other models are normally put. And it's a matter of just clicking on this button here, and you'd search out for it. If you go to the manufacturer's website, you look for either .IBIS or IBS. And when you bring it in, Altium's already going to match up the pin models with the schematic models, or the schematic pins. Okay? And they may give you some options here. Sometimes they do, sometimes they don't. It all depends on how the manufacturer set up this IBIS file. Okay? These things are locked in. There's a lot of things I can change over here. Okay? And that's fine by me, because that just means that the model that was provided by the manufacturer, they're very specific about it. So that's all you need is just drop it in, and Altium will match up the pins accordingly, assuming that your pins are correct in your schematic to begin with. And they should be, because if you got this from their data sheets, their IBIS file should match up accordingly. So that's what we've got over here. And again, you just add these in, as I've demonstrated, or briefly demonstrated. Now, how do we run the tool? Well, we can go over here to Tools. We go to Signal Integrity. The same thing exists on the PCB side as well. So I'm going to click on this, and Altium's going to do a review of things. Now, notice that it pulled up the PCB immediately, because if it sees a PCB, it wants to use that data, because that's additional trace length information, that's additional measurements that it has already available, real data that can be added to the model data. Keep in mind that an IBIS is just model data. It's an estimate, and what your board is providing is real-world information to be attached to that as well. Now, it's obviously going to show that not everything has an IBIS model. That's perfectly fine. I'm going to click on Model Assignment so we can just take a look at what Altium did with the net list. So every single component over here is listed, and there's certain things you got to worry about and certain things you really don't have to worry about. So, for example, capacitors and resistors, you don't have to worry about them. All you need to do is give them a value, and Altium will take care of the rest of them. So you don't have to put an IBIS model in for a capacitor or resistor. Altium will handle that. It'll also give you the status as to whether it thinks it has high confidence in the internal model. All right? Let's jump down to a few things here that look like they're changed. This one just says model found, right? Because it's an IBIS model. Altium doesn't know if it's a good one or a bad one. It just says, hey, look, I found the model. And in this case over here, there's probably no additional values that I can check. It just says, here's the model. This is how the pin outs are associated to the model itself, and that's all we've got. Okay? If we go down a little bit further over here, we may have something a little bit different. For example, the FPGA, they actually provide for something like typical, strong, and weak. Okay? So we've got different things. One of the things, we also have something like low confidence. These are test pins, so Altium's not sure if the model it has is the best model for this. So they give you the values, they give you the statuses, and you can also change things too. So if you're saying, no, this isn't high speed CMOS, you can change it to one of the other technologies. And once you've changed it, you don't have to bail out of this over here and go back into the schematic. You just simply click over here, check on it, and then you say update the model and the schematic, and it'll take care of that all for you. So it's kind of a nice way of doing ECOs without having to bail out of this and going into the schematic and making changes on each and every individual component. Okay? Now, let's go back to the FPGA here for a moment, because the FPGA is different, as I mentioned earlier on. The FPGA has options, okay? And we got to learn how to deal with the options. Let me cancel out of this, and I'll give you a very brief overview of it. To deal with the FPGA, there's two ways to do it. One of them is to go into Tools, FPGA Signal Manager. And what the Signal Manager will do is it will actually look at the constraint file that you provided, okay? And you can see that over here for this data bus, D0 to 31, we have information that was provided. The other stuff wasn't provided, so Altium's not going to make a guess at it. But what's nice about this is that Altium will actually let you go in here and make changes to these things without changing the constraint. And it's just a matter of clicking on this and doing an ECO over to the constraint file. The other way to do this, and though it does require a .fpga project, which we got to get to this thing called a constraint file. And if I bring it up over here, this constraint file is basically like your .ucf if you're doing, if you're basically doing like Xilinx, right? The .ucf is a user constraint file, and Altium has its own universal version of that for different FPGAs. So if we look over here, for example, on this record, we can see that Altium defines D31 to D0 based on these pins in the order in which they are listed, but it also shows things like the slew rates and the drive rates and even the signal or the standard. Now, personally, I like to do these in columns rather than long rows, but it still works this way as well. So if you change one of these, for example, if I did this and I say I'm going to make this 12 milliamps and I save it, okay, then when I go back to my signal manager, you'll see that that particular signal, let's see, 0, 1, 2, 3, 4, D4 should have 12 milliamps. there. So I can either change it in the signal manager or I can go to the constraint file and change it over there. Now, do you need to create this FPGA? Yes, you do. Okay, but it's not that hard to do, and actually there's a procedure. So if you're ever interested in doing this, please do, again, ask one of your sales reps. We can get you this procedure for making this very, very quickly. That's all you need to do. You don't have to do the whole FPGA and Altium Designer. And by the way, there's another really cool feature about this, and it's a little bit off on a tangent, but if you're doing a really large FPGA, there's a great wizard in Altium called FPGA to PCB Wizard. And if you set this up, and all this can be set up very quickly through SmartPaste, okay? You can set up the ports, you can set up the names, and what you can do is you can run that wizard, and Altium will basically create that sheet for you, okay? So if you've got a really, really large design, this is a very fast way to do it. So something to keep in mind. But we do need our constraint file in order to deal with the signal here, and I'll bring this back up here, the FPGA signal manager. So when I bring this up, we should now have a 12 in there. We do. In fact, there's another 12 here because I was playing with this earlier on. Okay. So that's just how to deal with the FPGA. Now, let's get to the meat of it. Let's actually run this thing. So let's go over here to Tools, Signal Integrity. Again, we're going to get the message that not all the models are found. We're going to skip that and let Altium just continue on. This is going to take about 2 or 3 minutes, all right? So Altium is actually going through right now where my cursor is at the bottom left. It is doing the analysis. It's looking at different things. It's actually pulling up numbers, believe it or not. And then one of the other things you're going to see is it's actually checking against the rules. And you're going to see in a minute that there's a set of rules that Altium provides for you to do this. And we'll talk a little bit more about that in just a minute. But we'll let this thing bring itself up, and then we'll display and explain that in just a moment. One other thing I'll mention is that this display that's going to come up is a panel, not a dialogue. And the cool part about a panel is that you can leave it up or push out to the side and continue to work in Altium Designer. Okay. All right, so now it came up. What do we got over here? It seems like it's kind of busy. Well, first and foremost, we have every single net in this design. You can see also we have a status over here. In this case, these weren't analyzed because there was no IBIS file associated to them. We also failed a few things. According to this, we seem to have failed the falling edge overshoot. We'll talk about that rule in just a minute. If we scroll down, we'll see some things that passed. Okay. So before we get into the reflection waveforms and the crosstalk waveforms, there's 2 thoughts there. First and foremost, you can see Altium took data. So when you kick that thing off, it was looking for real data based off the IBIS models and the tracks that you had on there. Okay? And then secondly, let's talk about, well, where did the rule come from that declared this thing to fail? Okay? And that's what I want to bring up right now. So I'm going to pull this off to the screen, and we're going to go over here to design rules. You think I know it by now. Okay? And you probably noticed this area in the rules called signal integrity, kind of at the very bottom. Well, that's where these start to come into play, and there's certain things you want to set up, because by default, Altium doesn't turn any of these on when you start a new board. But if you've got a design, you definitely want to declare the power for each one. It's not going to be smart enough to know what the powers are, so you want to tell it which net and its voltage. Okay? In addition to that, if you want, you can change the signal stimulus. Right? So Altium will use the default one, but if you want, you can create a new rule. I'll double-click into it so you can tell it whether you want a single pulse or if you want a train of pulses, start level, stop level, duty cycles, all that good stuff you can control over here if you want to tell Altium to use something different than its default. You can also create pass-fail rules here as well. And one of the things I really like about this is that it always gives you a really good little picture. So when it's asking for this, you can say, oh, this is this over here is what they're trying to measure. In this case, the max overshoot for falling. And what I did in my example is I said, okay, I'm going to give it 100 millivolts. Okay? And that's why we see this failure over here when I close that out and I bring this one back up. Okay? We failed this because these were all above 100 millivolts for the falling edge overshoot. So you can set those rules up accordingly. So one of the questions that may come to mind for you is this. Let me go over here to Tools, Design Rule Check. Can you use these rules during online DRC? And the answer is no, and I want to show that to you. The only 2 times I know of that you can use these signal integrity tools is if you kick off the signal integrity tool itself, which is what we did, or if you run the batch. Now, of course, the batch isn't going to do anything if you don't have IBIS models and if you don't have the rules set up. But if you click on this and you have these batch turn on, then it's going to try to run those. Okay, so that's the 2 times that the signal integrity tools can be run. But right now, Altium is not able to handle online. So as you're running along, it's not be able to say, no, your signal integrity is terrible, or by the way, here's what your signal integrity looks like once you finish a route. It can't do that at this time. Okay, but that's kind of, I mean, that's definitely something, I think definitely something far ahead in the future. Now, with all that being said, we want to look at some waveforms. Why didn't Altium create waveforms for this? Because if we told Altium to create waveforms for this, we may as well have kicked it off and then gone home, because it will take quite a long time for it to do that. So Altium says, I'm not going to try to do all the reflection waveforms. All I'm going to do is I'll do them if you tell me what you want me to do them on. Okay. So what I'm going to do is I'm going to sort this out, and I'm going to jump up to D0. Okay, so here's D0 over here, and it did fail. That's fine, but I also want to take a look at its reflection. All right, and by me doing this, what I can do is I can click on this and tell Altium, hey, let's analyze this net a little bit deeper. And you'll notice that the reflection waveform now has been enabled. We'll talk about the crosstalk one in just a moment. Once you bring this up, it says, all right, here are all these designators and their pins that are associated with this. One of the things we have to do here is we have to make sure that we declare one input and the rest of them to be the output. Okay? So, because it needs to know which IBIS model it's going to use to drive out and which IBIS models are going to be to drive in. So I'm going to toggle this one as being the output. And by the way, notice my schematic will jump around as I'm doing this. Okay, and I'll make this one an N. These are fine the way it is. So I'm saying from U1 they're going to U5, U8, and U9 for D0. I can also do different analysis here. I can do no termination. I can also do series resistance. And what's cool about this, if you can see it, maybe I can pull it down just a little bit more so you can see it. I can also tell it a min and max resistance to try this against, and so it will test these with different resistors. Now, if you find one that you like, that means that you're going to ultimately have to go to the schematic, add that resistor in, then push it over to the PCB side and add the footprint in. But at least it will do this so you don't have to go through all that work of trying each and every single resistor. Okay. Once I've got this set up, I'm going to hit the reflection waveforms. Okay, and then I'll move this out of the side here so you can take a look. So because we set this up, we ask for no termination. And what's cool about this, when I click on it, all the other ones correspond with it. And as I go down for each one of them, so we have to do 10 passes over here. Here's the resistor at 25. Here's at 38.9. So I can take a look at how each one of these are responding based off of what I put in there. This doesn't seem to be any reflection, so that's certainly a good sign. Now, in addition to that, if you're familiar with this screen, it's the exact same screen that you use for SPICE. And as a matter of fact, you can put the cursors up here. So I'll put cursor A up here, and I'll just drag it over here. So if I want to see certain values, and I can put cursor B up here. And the reason I can do that is because Altium has another panel that we can use, and it's called the SIM data. So as I move A and B, it gives me data, which is really kind of slick. All right. And so again, these two things that you're looking at where my cursor is, these are also available on the SPICE side as well. So if you're familiar with SPICE and Altium Designer, you don't have to learn a new editing tool. The charts, plots, and waves work the same way. The SIM data tool works the exact same way, which is really nice. Now, with the time I've got remaining here, and it's going short as usual, so much great stuff to show you here. Let me go back to my panel and do the crosstalk. So the crosstalk's a little bit different because, and the reason why Altium needs a PCB is because it needs to have an aggressor and it needs to have victims. Sounds kind of tragic, okay? But that's what we need to do because that's what crosstalk's all about, is trying to understand if I got a noisy signal, how is it impacting my other signals around it. So I'm going to pick on D5 over here. Let's bring up D5, okay? And Altium has a tool in here where I can right-click and I can say find coupled nets. Now you can set up preferences so it can find them based on a certain range. Because my time's limited here, just assume I've already got my range set up. So when I've got my coupled nets, Altium's going to come back and say, look, these two nets, based on your criteria and your preferences, say that these are very close and you should investigate all of them. So I'm going to click my magic button here and say, Altium, I want you to deal with these. Okay, and then I'm going to do the crosstalk waveform. Okay. Oh, and I forgot the most important part. It needs to know who the aggressor is. So I can right-click over here and I can tell it to set the aggressor. It immediately sets the victims. Okay, and now I can click on my crosstalk, and it'll bring it right up here, and I'll pull my panel out of the way in just a moment. Let it finish up here. And keep in mind, the reason why it's taking a little bit of time to do this is because I turned on both of these here. I turned on no termination and with the series resistors. So it's actually doing the analysis of the crosstalk based on all of those. Let me pull this down over here. And again, same thing I've got. I can click on this, and these other ones are going to be highlighted. So if I want to see what's going on with these different things, I can. all right, and with the different resistors that I've got on it, and so on and so forth. That's what I got for you. Just one last thing I may show you over here with the fail report, which I think is very useful. You've noticed that we had the failures here earlier on, so if you set up your rules, it's one thing to go through here, but Altium also provides a display report, which is really slick. I'll just move this out. It'll basically show you all those things that failed, what the tolerances should have been, and what they failed at. So it's a very quick way to get information, especially if you're doing any type of scripting.